In this lesson, we're going to examine the symmetry of relations and functions. So when we look at relations, there can be two types of symmetry present, line symmetry or point symmetry. If a relation has line symmetry, the graph can be folded along a line so that the two halves match perfectly. Whereas if a relation has point symmetry, the graph can be rotated 180 degrees and the graph can appear as if it is unchanged. Here are the three most common types of symmetry that you will encounter in relations and functions. Okay, so the first type is symmetry along the x-axis, okay? So the graph of a relation is symmetric with respect to the x-axis if and only if for every point x, y on the graph, so right here's x, y, what do we have to have as well? We have to have it flipped across the x-axis, so that's going to make your y be the opposite sign. So you would have x negative y is also on the graph. Now, algebraically, how do you test? Well, what you do is you replace y with the opposite of y, and it produces the exact same equation when you simplify it. Okay, second type of line symmetry you're going to see is symmetry with respect to the y-axis. So it has this type of symmetry if every point on the graph, which we call xy, so every ordered pair right here, also has a corresponding point the opposite of x comma y on the graph. So the opposite of x comma y. Now the algebraic test for this would be to replace every x with the opposite of x and you'll get the same equation. And the third type of symmetry would be symmetry with respect to the origin. So the graph of a relation is symmetric with respect to the origin if and only if for every point x, y, there is also a point on the graph the opposite of x, the opposite of y. And let's talk about the algebraic test for this. Replacing both x with negative x and y with negative y produces an equivalent equation. The directions here say use the graph of each equation to test for symmetry with respect to the x-axis, y-axis, and the origin. Support the answer numerically and confirm algebraically. We're going to focus just on confirming algebraically here. When I look at this, I see symmetry with respect to the y-axis. If I fold it along here, I'm going to get one half to fall directly on the other half. I mean, confirming it numerically would be pick a point. If I pick this 1, 1, the ordered pair 1, negative 1 is also there. If I pick another ordered pair, down here, this is approximately, it's not exactly, negative 4, negative 8, positive 4, negative 8 would also be there. Okay, so my algebraic test. Algebraically, what we need to do is replace everywhere there is an x with a negative x. And we should get the same or an equivalent equation when we clean this up. So if I square negative x, that's going to switch back to a positive x squared. Now I just bring down this negative that was out front, plus 6. Look, I get the exact same equation. In this second one, I have a perfect circle. I'd like to point out that this would be a relation, not a function, because it would fail the vertical line test. When I look at this, I believe I'm going to have y-axis symmetry. Would also have x-axis symmetry. And I could rotate my graph 180 degrees, or like turn your paper upside down would be another way of saying that. And I'm going to have the exact same picture. So to confirm this algebraically, I'm going to need to plug in, for x-axis symmetry, I plug in the opposite letter, negative y for y, and when I square negative y, I get exactly what I started with. So I've got x-axis symmetry. To confirm symmetry with respect to the y-axis, I plug in negative x. When I square that, again, I get this exact same equation. And for symmetry with respect to the origin, I need to replace both letters with their opposites. And again, when I square both, I'm going to get back to two positives. So I have algebraically confirmed that I have all three types of symmetry. In this one, I do not believe that I have line symmetry here, but I do have symmetry with respect to the origin. And with respect to the origin, I am replacing both letters with their opposites. And sure enough, I get what I started with. How do I see it? Just by looking at it, if you rotate 180 degrees or flip your paper upside down, you get the exact same graph. It looks unchanged. It's still in the first and third quadrant. Now, relations can have symmetry across the x-axis, but functions cannot. So when I am looking just at functions, functions can only have y-axis symmetry or symmetry with respect to the origin. So I'm going to fill in those two words there, y-axis or origin symmetry. Now, if they have this type of symmetry, they're either going to be even functions or odd functions. So functions that are symmetric with respect to the y-axis are called even functions. So ones that are symmetric with respect to the origin, these ones are going to be odd. Now, I don't want you to think that all functions are exactly even with this type of symmetry or exactly odd with this type of symmetry. There's a lot of functions that don't fall into even symmetry or odd symmetry. The test is really the same as what we mentioned before. So for an even function for y-axis symmetry, what are we doing? We are replacing the opposite letter. We're replacing every x with the opposite of x. So we do f of negative x, and what happens? We have to get the exact same equation that we started with is equal to f of x. Now, if it's an odd function, what do? Well, we replace again x with negative x, but what we end up with is the exact opposite of our original function. So if we had all addition signs in our original function, we're going to have all negative signs in our new function. Now when I look at this first one, f of x equals x cubed minus 2x, just want to kind of get a hint from it. I have an odd exponent, so my gut feeling here is telling me if there's any type of symmetry, it's probably going to be odd symmetry. So in the graphing calculator, go ahead, pause the video, hit y equals, and graph this function. I'm going to do a quick sketch. My graph looks something like this when I graph it on my standard viewing window with a scale of -10 to 10 and on the y also -10 to 10. So looking at this, it looks to me like I have symmetry about the origin. I'm going to check for odd symmetry. So how do I do this? Well, I take my original function and I'm substituting in negative x everywhere there was an x. So I'm just opening up parentheses, and everywhere there was an x, I'm going to replace it with negative x, and I'm going to clean this up now. So negative x to the third power is going to produce negative x to the third. When you raise a negative value to an odd exponent, it will always be negative. And then I have negative 2 times negative x would be plus 2x. So when I look at this, how does it compare to my original? Well, everything is exactly the opposite sign. So what do I do just algebraically? One last step is I factor out a -1 here. Think of the greatest common factor, which will switch each sign, and there I've got it. So I have exactly that f of negative x is equal to the opposite of my original f of x. So this confirms that I have odd symmetry. Algebraically proven it. Next, again, I'm going to sketch this function. Please take the second to type it into your graphing calculator. Kind of looks like a parabola, but it's wider. And at a glance, again, it looks like I have symmetry this time across the y-axis, which I'm not really surprised because I've got an even exponent here, so my gut feeling tells me, if I'm going to have symmetry, it's going to be even symmetry. So I'm going to do my algebraic test, which is, again, everywhere there is an x, I'm going to replace it with the opposite of x. All right, and algebra, to clean this up, negative x to the fourth is the same as x to the fourth plus 2. So how does this compare? Well, it's identical to what I started with, so I can say that f of negative x is equal to f of x. So I do indeed have even symmetry here. In this third one, again, we are going to check for both even and odd symmetry here. So looking at it, I see both an even and an odd exponent, but the highest degree is 3. So gut feeling says, if I'm going to have symmetry, it's probably odd, but again, the tests start the same way. You plug in the opposite of x everywhere there is an x. So I just take my function and I open up parentheses everywhere there was an x, and I'm going to use a little algebra to clean this up. Now, what I didn't do, though, I just realized, is I didn't graph it on my graphing calculator. So why don't you pause and check what the graph looks like? My graph looks something like that. So there's a possibility perhaps I do have odd function or odd symmetry here. So let's keep going. So when I raise negative x to the third power, that's going to be negative x to the third minus 0.5. I need to square this is going to produce positive x squared, and then plus 3x at the end because I have a negative times a positive. Now, how does this compare? Well, it's not identical to what I started with. Let's see if it's the complete opposite. Well, did every sign change? No, the first and last did, but the middle did not. So if even if I factor out a negative this time, x cubed plus 0.5x squared minus 3x, does that equal what I started with? Nope. So I'm going to say h of negative x does not equal the original h of x, nor does it equal the opposite of h of x. I'm going to say, therefore, neither even nor odd symmetry.